Section: Introduction. In this section, we explore the creation of lifelike 3D head avatars, which are useful in various fields like telepresence, film, personalized gaming, and digital education. Traditionally, making a high-quality avatar requires lengthy studio recordings with expensive setups, which limits its use, especially for casual users who may only have a few smartphone images. We introduce Avat3r, a method that allows us to create an animatable 3D head avatar from just a few images. This task presents several challenges. First, sparse 3D reconstruction is tricky because some areas, like the inside of the mouth or the sides of the head, might not be visible in the images we have. Second, animating the head involves creating realistic movements without having seen the person in action. Lastly, the input images may not be consistent, as the person might not stay still during capture. To tackle these challenges, sparse reconstruction, face animation, and robust reconstruction, we need to solve them all at once. Current top methods for high-quality avatars can't be used because they require many more images than we have. Other methods that animate 3D portraits learn from large video datasets but often focus on frontal views, sacrificing 3D and temporal consistency, making them less suitable for scenarios needing a proper 3D model. We also consider building a photorealistic 3D head model that learns from existing 3D face datasets, which are limited in diversity. Our approach is based on the idea that while 3D face data is limited in identity, it is rich in expressions. Thus, we create a system that is tailored to a person's identity but can generalize across different expressions. Unlike traditional models, our network doesn't need to learn every detail of human facial appearance. It just needs to reconstruct it from a few images, simplifying the task. We draw inspiration from recent large reconstruction models and design an architecture that predicts 3D Gaussians for each pixel in the input images. We avoid using a fixed template mesh for these Gaussians because human facial features are complex and varied. For instance, a person with thick hair will need more primitives than someone who is bald. To make sparse 3D reconstruction easier, we first generate position maps for each image using Avat3r. These maps are integrated into our network through skip connections, providing a rough starting point for each Gaussian. We find that Avat3r can still produce useful position maps even when the input images are inconsistent, such as showing different expressions or being generated from varying viewpoints. This capability allows us to train our model on images taken at different times, enhancing its robustness to inconsistencies that can arise in real-life scenarios. Finally, for face animation, we discover that simple cross-attention between feature maps and an expression code is enough to capture a range of facial expressions. In summary, we present Avat3r, a new pipeline for quickly creating high-quality 3D head avatars from just a few images. We also introduce the first animatable large 3D reconstruction model and demonstrate that basic cross-attention on expression sequences can effectively model complex facial animations. To boost generalization and robustness, we incorporate insights from Avat3r and Sapiens through skip connections and train with images from different time points. Section Summary. In this section, we introduce Avat3r, a novel method for creating high-quality, animatable 3D head avatars from just a few casual images, addressing challenges like sparse 3D reconstruction and facial animation. Our approach leverages position maps and cross-attention mechanisms to enhance generalization and robustness, enabling the reconstruction of realistic avatars quickly and effectively. Section: Related work. In this section, we discuss related work in the field of 3D reconstruction and animation. Recently, generalized feed-forward models for 3D reconstruction from sparse views have gained significant attention, especially in challenging scenarios. The Large Reconstruction Model, LRM, utilizes a transformer-based encoder-decoder system to create a NeRF reconstruction from just one image. Newer models have focused on generating 3D Gaussian representations from 4 images, achieving impressive results in synthesizing novel views. The transformer-based approach has also been applied to convert monocular videos into 4D representations. However, Existing research has not explored creating animatable 3D representations from sparse images, which is our primary focus. We build upon the large Gaussian reconstruction model, GRM, for this purpose. Another area of research involves animating portraits in a 3D-aware manner. For instance, Mega Portraits constructs a 3D volume using a source and driving image, rendering the animated actor through orthographic projection and 2D neural rendering. 3D morphable models, 3DMMs, are commonly used to provide better control over portrait animation. For example, StyleRig shows how a 3DMM can manipulate data from a pre-trained StyleGAN network. Rome predicts changes in vertices and textures of a flame mesh based on the input image. Various methods like Portrait 4D and GP Avatar animate a triplane representation using flame. Other approaches, such as Voodoo 3D, develop their own expression encoders for more detailed animations. All these methods require only a single image to animate a person, allowing them to train on large monocular video datasets to learn a general motion prior, applicable even to paintings or cartoons. However, they often prioritize image quality over 3D consistency by using 2D screen space renderers. In contrast, our work aims to create a complete and accurate 3D avatar representation from input images that can be viewed from any angle. The rise of large-scale multi-view face datasets has facilitated the development of photorealistic 3D face models that capture detailed geometry and appearance. For example, HeadNerf conditions a neural radiance field on various factors like identity and expression. VRMM creates high-quality, relightable 3D face models using volumetric elements. 1.2 Avatar enhances a 3DMM by linking a radiance field to its surface. More recent models like GPHM and HeadGAP use 3D Gaussians for photorealistic face modeling. These models learn a strong prior on human facial features, allowing them to fit a 3D head avatar from one or more images. However, the fitting process can be complex and often requires costly optimization, making it impractical for everyday use on standard devices. While a generalized encoder could help, a key limitation remains. The number of training subjects is often limited, making it difficult to capture the full range of human facial appearances. Our approach addresses this by conditioning on specific images of a person and generalizing only over expressions, where we have ample data. Recent work on codec avatars has also aimed to create animatable 3D representations from registered meshes, but these methods often require extensive video capture and costly optimization. For instance, Avatar fine-tunes their network on video recordings for hours on powerful GPUs, making it unfeasible for consumer devices. In contrast, our method directly generates a 3D head avatar from just 4 images without the need for expensive fine-tuning. Our goal with Avat3r is to predict a high-quality 3D Gaussian representation of a human head from a few posed images while animating the head to match a desired expression. We define this process as taking input images, their camera parameters, and a code for the desired expression. In our experiments, we use 4 input images. Importantly, these images do not need to come from multi-view systems. They can be from different moments in time, allowing us to train and infer from frames of monocular videos. Avat3r employs a vision transformer backbone to predict 3D Gaussian primitives for each pixel in the input images, and we will now introduce the various components of our pipeline. Section Summary. In this section, we review recent advancements in 3D reconstruction models, highlighting the shift towards transformer-based approaches that can generate 3D representations from limited input images. We also discuss the limitations of existing methods in producing animatable 3D avatars and introduce our approach, Avat3r, which predicts high-quality 3D Gaussian representations from just 4 posed images while enabling facial expression animation without the need for extensive fine-tuning. Section: Pre-trained foundation models. In this section, we simplify our task by using 2 foundation models, Dust3r and Sapiens. Dust3r generates dense position maps for a set of input images and aligns them with known camera parameters. These position maps help us place 3D Gaussians. Meanwhile, Sapiens provides a detailed low-resolution feature map for each image, which aids in the view matching task performed by the following transformer. We define the position and confidence maps predicted by Avat3r as I position and I confidence, and the feature maps from Sapiens as I feature. For our animatable large 3D reconstruction model, we adopt a vision transformer architecture similar to GRM. We start by breaking down the input maps into patches using a convolutional layer. Here, I_pluck represents the per-array plucker coordinates for each pixel, and H becomes the low-resolution intermediate feature maps for each input view. Next, we integrate the pre-computed feature maps from Sapiens, transforming them to match the resolution of our intermediate feature maps through grid sampling. We then use a linear layer to reduce the dimensions of the concatenated feature maps to avoid excessive computation in the subsequent transformer layers. The core of our vision transformer includes several self-attention layers that facilitate cross-view matching among all tokens to extract 3D information from the input images. To make Avat3r animatable, we add cross-attention layers that allow each image token to connect with a sequence of expression tokens. The MLP projects a single expression code into a sequence, and by enriching each image token with this expression-dependent information, Avat3r can model complex 3D facial animations. We then upsample the image tokens back to the original input resolution using a transformer-based UP sampler. The resulting Gaussian attribute maps contain per-pixel information such as positions, scales, rotations, colors, and opacities. After upsampling, we add skip connections for positions and colors to ensure that each pixel generates a 3D Gaussian that reflects its corresponding geometry. Finally, we utilize Avat3r's confidence maps to determine which pixels in the generated Gaussian attribute maps should create a 3D Gaussian. We set a threshold for minimal confidence, which helps prevent artifacts from incorrect initializations and adjusts the number of Gaussians based on the individual characteristics of the person, similar to foreground segmentation. For instance, if a person has voluminous hair, more pixels will be classified as foreground, resulting in more retained Gaussians. Section Summary. In this section, we utilize two foundation models, Avat3r and Sapiens, to generate position and feature maps from input images, which facilitate 3D Gaussian placement and view matching. We then implement a vision transformer architecture that incorporates these maps to enable animatable 3D reconstructions, using confidence thresholds to refine Gaussian generation based on pixel relevance. Section: Losses. In this section, we discuss the losses used in training Avat3r. We can train Avat3r using only photometric losses for new viewpoints, similar to the original 3D Gaussian splatting approach. We define two main loss functions. The first measures the difference between the rendered image and the ground truth image, while the second assesses the structural similarity between them. Additionally, we include perceptual losses to enhance high-frequency details, which compares the rendered image to the ground truth in a way that captures perceptual differences. The overall loss we use combines these three components, each weighted by specific factors. The first loss has a weight of 0.8, the second has a weight of 0.2, and the perceptual loss has a weight of 0.01. For training, we utilize multi-view video captures from the Avat256 dataset, specifically the 4 TB version that includes videos at 7.5 frames per second from 80 cameras, with each video containing about 5,000 frames at a resolution of 1024 by 667 pixels. We train Avat3r on 244 individuals from this dataset, keeping 12 individuals aside for testing. We crop each image to focus on the head, creating a 512 by 512 portrait for input. For each training instance, we randomly select 4 diverse viewpoints and 4 different expressions as input images. The ground truth images are kept at the highest resolution and sampled randomly from all cameras and timeframes. We use expression codes provided in the dataset for our model. We train Avat3r using the Atom optimizer with a learning rate of 0.00005. We introduce the perceptual loss only after 3 million optimization steps to prevent early focus on high-frequency details. The total training lasts for 3.5 million steps, with a batch size of 1 per GPU across 8 A100 GPUs, taking about 4 days. We find that training is more effective when we supervise multiple viewpoints in each batch, meaning each batch consists of 12 images, 4 for input and 8 for supervision. Our task is to evaluate how well we can create a 3D head avatar from one or more images of a person we haven't seen before. To measure the quality of the rendered images, we use 3 metrics: peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, and learned perceptual image patch similarity, LPIPS. We also assess the visual similarity of rendered videos to their ground truth counterparts using the perceptual video metric JOD. Additionally, we employ 2 face-specific metrics: average keypoint distance, AKD, in pixels, estimated from PipNet, and cosine similarity, CSIM, of identity embeddings based on ArcFace. We compare our method against recent state-of-the-art systems for creating 3D head avatars from one or a few input images. One baseline is GP-Avatar, which uses a NeRF-based approach to predict canonical triplanes from multiple images and models animations by querying 3D points in an expression-dependent feature field. Another baseline is GAG-Avatar, which constructs 2 sets of 3D Gaussians from a single image for 3D-aware portrait animation. We specifically compare our ability to create a realistic 3D head avatar from just 4 images against GP-Avatar. We train GP-Avatar on the Avat3r dataset under the same conditions as our model, using high-quality tracked meshes from the dataset. We evaluate both methods at a resolution of 512 by 512 pixels on the same 12 holdout individuals, sampling 1,000 different target expressions from various viewpoints. For the JOD metric, we render a video of 100 frames from the frontal camera for each holdout person. The results show that our method significantly outperforms the baseline, particularly in metrics related to alignment, temporal consistency, and identity similarity. This suggests that Avat3r creates 3D head avatars that closely resemble the individuals in the input images and produces smoother video renderings without needing a screen space super resolution network like GP-Avatar. We also provide qualitative comparisons, showing that our method generates more expressive avatars with better rendering quality than the baseline, even for individuals with colored hair and headbands. To further evaluate Avat3r's generalization, we create few-shot 3D head avatars for subjects from the NeRF dataset, which we did not use during training. The results indicate that Avat3r can still produce realistic 3D head avatars in this different setting, despite the varying lighting, camera parameters, and viewpoints compared to the Avat3r dataset. Section Summary. In this section, we describe the training process for Avat3r, which utilizes a combination of photometric and perceptual losses to enhance high-frequency details while being trained on multi-view video captures from the Avat3r dataset. We evaluate our method against state-of-the-art systems, demonstrating that Avat3r outperforms baselines in creating realistic 3D head avatars from limited input images, even generalizing well to unseen datasets. Section: Single-shot 3D head avatar creation. In this section, we discuss our approach to creating 3D head avatars from a single image using Avat3r. We utilize a pre-trained 3D GAN to convert the single image into a 3D model and generate 4 different views of the head, which we then input into Avat3r. We compare our method with the recent GAG-Avatar technique, specifically 2 versions, one from the original authors trained on the VFHQ dataset and another that we trained on the Avat3r dataset. For GAG-Avatar, we use their monocular flame tracker to obtain tracked meshes. Our qualitative comparisons, shown in a figure, reveal that our method performs well against single-input baselines, even though we did not train specifically for single-shot scenarios. We observe that Avat3r generates more realistic facial expressions compared to GAG-Avatar, which is limited by the expression capabilities of Flame. Additionally, our method allows for more extreme changes in viewpoint without losing rendering quality. Next, we evaluate the effectiveness of our design choices for Avat3r. We examine the impact of Avat3r's position maps, the Sapiens feature maps, and the use of input images with varying expressions during training. Our findings indicate that removing Avat3r significantly reduces geometric accuracy, as seen in our ablation studies. The Sapiens feature maps enhance the semantic richness of the input images, leading to sharper predictions, particularly in areas like hair. Training with consistent input images yields slightly sharper results, but inconsistencies can introduce artifacts in the generated 3D representation. We also explore several applications of Avat3r, including generating a new 3D head with GG head and animating it, creating a portrait image with a text-to-image model, and lifting an existing photograph for animation. Our results show that Avat3r can be effectively used in various casual scenarios, suggesting that it can animate images from any 3D GAN that produces 3D heads. Despite Avat3r's strengths, we acknowledge some limitations. The current process for creating avatars from a single image relies on a 3D GAN, which can introduce errors by not perfectly capturing details and by using NeRF-based methods that may lead to inconsistencies in the final images. These issues may improve as better 3D GANs are developed. Additionally, our framework requires camera pose estimates during inference, which can lead to errors if the estimates are incorrect. We consider potential solutions, such as training the network to handle inaccurate camera poses or eliminating the need for them altogether. Lastly, our current setup does not allow for control over lighting, which can make avatars appear out of place in new environments. Addressing lighting properties is a promising direction for future research.